So, hi everyone, my name is Hristo, and today I'm going to tell you some interesting things about multitask learning in the real world with the Catalyst framework. This presentation is part of the Catalyst workshop at the DataFest. So, first I'm going to just quickly tell you what is the basic idea with multitask learning and what we are trying to achieve with it and why it has so much business value. Then I'm going to tell you why I chose Catalyst for multitask learning projects when I face them at work. Then I'm going to walk you through a case study of a hypothetical surveillance project. We're going to work with a synthetic dataset for quick convergence and to avoid any possible dataset issues. And then I'm going to tell you a few possible applications after we have understood basically how we can use multitask learning with Catalyst. Then in the end I'm going to just discuss object detection with you and how we can see it through the multitask lens, and then I'm going to give you some links for further study, to stay in touch, and some the talks on which these utilities are based, and then of course some time for questions, but you can stop me at any time and ask in the spatial chat. So what is the basic idea with multitask learning? The basic idea is that you have a single neural network which has a large shared backbone, and then it has task-specific subnetworks, and then in the end the network has multiple outputs for different tasks. This is the basic idea. The big advantage of this approach is that the computational savings and memory savings as well are huge. So for stuff like autopilot at Tesla, or in general in the car industry, in the automotive industry, obviously, because you're deploying the neural network on some sort of embedded device, you can't afford to have a separate neural network for every single task. And even if you're not working in an embedded environment, if you're working in a cloud environment and deploying your services there, it's still going to be cheaper to deploy one neural network for several tasks. So there are different types of multitask learning. The main two types are hard or soft parameter sharing. I'm going to tell you in the next slide what is the difference between them. Multitask learning typically reduces the risk of overfitting, because then the shared backbone is trained on a lot of different tasks, and its ability to generalize is a lot better. But there are complex relationships. So there are papers which show that sometimes some tasks actually interfere with the learning for other tasks. So this is not 100% true, but typically it does reduce the risk of overfitting. And one interesting thing is that you have lots of multiple outputs for the different tasks, but sometimes one of the tasks may be a precondition for another. We're going to see an example for that and how we're handling it. Then there is this thing of managing an evolving multitask learning project, so continuously adding new precondition tasks and so on, which are requested by the business people, for example. And this could get really difficult if you don't have a really solid training loop framework, because there is a lot of stuff that could go wrong. And lastly, I would like to quote Lex Friedman, who says that most real-world problems are multitask, and he also said that it's a very understudied field currently. Those are his words which were, he commented them on the presentation of Andrei Karpathy at the ICML last year. So the two types of multitask learning are with soft parameter sharing, which is on the left on this slide, and hard parameter sharing, which is on the right on this slide. So in hard parameter sharing, you basically have a large backbone which is completely shared between the tasks, and then you have just a bunch of task-specific subnetworks and task-specific heads. In soft parameter sharing, the backbones are not necessarily exactly the same. Usually there is some sort of restriction on the weights, so that the weights are relatively close, but in this presentation we're going to focus almost entirely on the right picture, so on the hard parameter sharing. So why I chose Catalyst for this project? So there are lots of training loop frameworks in PyTorch, and I chose it because for several reasons. First, its main focus is on reproducibility, which is very important in multitask learning setting. The one thing that I really like about the API of Catalyst is that it works with PyTorch classes directly, so you don't need additional abstractions. So for example, in PyTorch Lightning, you have to extend their own version of PyTorch Lightning module, which I personally kind of dislike, because it has a feeling of locking you in their framework. So for example, if I take something from any GitHub project or whatever, then I would have to first think, how do I convert it to a PyTorch Lightning module? And this is something that I kind of disliked. Obviously, you can do the same thing with both frameworks, since they're both doing the same thing in the end. They're both training loop frameworks, but this is something that I really liked in Catalyst, and the reason that I chose it over PyTorch Lightning. Catalyst has lots of nice features. Some of them include really nice out-of-the-box half precision support and data parallel support. So no need to manually tweak Apex, which used to be a very unpleasant task, at least for me. There's lots of weird issues that can happen, like not in numbers and weird stuff that could happen. So it's nice to just have the framework handle this for you. Catalyst has lots of nice defaults, automatic TensorBoard logging, and a great list of built-in callbacks, a simple API for implementing your own. So it's very extensible. The code is really well written and very easy to understand. So if I sometimes have to tweak it a bit, it's really nice, and it's very extensible. And also, obviously, there is an active Slack community for asking questions, which is really important. Okay, so let's start with the case study. So let's say that your next project is to create a surveillance camera for a factory, and the business guys has said that they want to detect faces and the bodies of people. Maybe they want to check the uniform on their body and do facial recognition on their faces. So the first step would be to find a model which can predict the bounding boxes, for example, in XYWH format. So this means that the output of the network would be the top left point in XY, and then the width and height of the bounding box. And if you treat this as a linear regression, so with a mean squared error, and you use some sort of fancy pre-trained model for this, maybe some sort of retina net, or some sort of fancy model you have found online, and in the end you have a regression head for X, Y, W, and H. So you found them, and here are an example images from the synthetic data set. Basically, the rectangle is the body and the circle is the face. So yeah, in this case study, I'm going to show it through a synthetic data set to avoid any sort of personal data issues, and for quick convergence, and so that you can quickly see what is going on. So we have to create our own PyTorch NN module, which is the standard stuff. We basically extend the NN module from PyTorch. Then we use our own fancy feature extractor or whatever. And then we have regression heads, which are, in this case, are fully connected layers for face and body, and they predict 4 different coordinates for x, y, w, and h. And the output is a dictionary with the logits for the face regression and the body regression. So here we have the loss function would look something like this. So it would be a weighted sum of the different loss terms. Here, for simplicity, I'm just summing them. But obviously, in a real-world project, you want to also put some weight on tasks which are more important. So next, we have to create our dataset class, which is then, as usual, in PyTorch. So I haven't prepared an example here. Then we have to split our dataset into train, validation, and test, and then we have to create an ordered dictionary with the data loaders from the datasets above, and this ordered dictionary has to have train, valid, and test. Actually, for training, even train and valid are sufficient. So then we have to add catalyst callbacks. By default, Catalyst has a callback which logs the loss to the TensorBot, but we also want to do early stopping based on the DOS function, and Catalyst has a built-in support for this. We just use the early stopping callback, but we also want to log the loss for every regression separately, so that if there is some problem, we have to be able to see which task is causing the problem, right? So we also plot the mean absolute error for both regression tasks. And the next step would be we create our supervised runner, and we just call runner.train, and we pass in the model, the criterion, the optimizer, the loaders, which I mentioned already, the callbacks, which I also mentioned, the log dir. This is where the checkpoints will be saved, and also the TensorBoard data would be saved, the maximum number of epochs, whether you want verbosity, and if you want FP16 support. Okay, so after we've done that, we want to evaluate the results. We want to inspect them. So apart from looking at the metrics at the TensorBoard and creating data frames with different reports, comparing it to different models, we also want to have a look at the best and worst examples per task. So one way this could be achieved is by calling the original loss without reduction and then reducing from dimension 2 onwards. This way we're going to get an array with the same length as the number of examples in the dataset, and we're going to have a numerical value which tells us how wrong the model was in his predictions for this particular sample. And after we sort this, we can see which are the best and which are the worst examples in the dataset. Okay, so let's say we've done that, but then we have to take into account that there isn't always a person there. So we first have to have a binary classification branch, and only then we have to predict the face regression and body regression if a person is present. So basically we have to update and maintain this dependency person present is a parent task to the face and body regression, and face person present is also acts as a precondition of the face and body regression, and this dependency has to be maintained at several places. What are some examples? For example, we have to include the ground truth for the parent tasks in the batch. We have to update the weights for the child task only when the parent is true in the ground truth. When training, we have to compute the loss for the child task only when the parent is true in the ground truth. In the callbacks, we have to update the metrics for the child task only when the parent is true in the ground truth. When we're doing inference, we have to activate and decode the parent task before applying the task to the child task. So here what I mean is, for example, if you have the binary classification task, you have to apply a sigmoid to it and then threshold it so that you get a mask, a Boolean mask of true and false values, and then you have to apply this mask to the child task. Then when we are doing results interpretation, which is finding the best and the worst in the validation data set, we have to apply this preconditioning as well. And then when we're inspecting GradCam or any other visualization method per task, we have to apply the preconditioning and this flow of tasks as well. And also when we are doing selecting thresholds for binary tasks, we also have to apply this precondition. Remember, the binary task can by itself have a parent, another task. And let's say you have updated all of those by hand, but then the business side wants to make this more involved. So first they want to classify if the camera is blocked, because maybe in the factory when thieves come in, they just put something which blocks the camera view, and then the camera doesn't notify anyone for this. So we have to first classify if the camera is blocked. Then if the camera is not blocked, we have to see if the door of the factory is open. And if it's not open, meaning that the door is closed, then we have to check if the door is locked, so that it can notify someone that, okay, the door is closed but it's not locked yet. And then if the door is opened, then we have to check if there is a person present, so call this binary classification branch. And then finally, if the person is present, we have to find and do this face and body linear regression tasks. And in the end you end up maintaining this whole tree of preconditions in 8 different places. And not only does it violate the right principle, it gets really hard to maintain if you really want to have this interpretation per task and all those different methods for evaluating and in general working on this multitask project. So one idea could be to create task and task flow abstractions. We take care of these dependencies at a single place, and then you can create a loss function that respects the preconditions automatically. So this is the abstraction that I have made of a task. So for example, you have the name of the task, the labels of the task, the loss function, the per sample loss, which is the loss function that we're going to use in order to be able to get a per sample loss value, so that we can interpret which are the best and which are the worst samples. The available function filters missing values. So for example, if we don't have a label for this specific sample, we want to obviously skip the gradient update. We have the inputs for the task, then we have the activation. For example, for binary classification task it would be sigmoid, for normal classification task it would be softmax, and so on. The decoder depends on the task. For example, an example would be for binary classification, the decoder would be just thresholding. A module, which is the task specific part of the network, and this allows you to do stuff like setting the learning rate for a specific task to be different, and also freezing the backbone and training only those specific weights. And another way, and another thing that we also have to supply is the metrics. So here we have it's a tuple of string, the name of the metric, and the torch metric, which is basically the torch metric is a wrapper of the usual metric, which handles the precondition correctly. So, and this is how an example task flow looks like. So it has 3 parameters. Flow is something in which the tasks are already registered. The list of tasks is already registered. X is an input dictionary of features. So if you have different features for different tasks, you would have multiple keys and values. Here only one key is present, the features key. And out is the thing in which we accumulate the result. And you can see here the flow that we described in natural language translated to this small DSL-like function. So first we predict if the camera is blocked, then we predict if the door is open, given that the camera is not blocked. Then we predict if the door is locked, given that the door is not open, and then we predict if a person is present, given that the door is open, and finally we do the person regression task, given that the person is present. So now let's Let's have a look at a quick demo of a Jupyter Notebook and we'll continue. Okay, great. So about the demo, so I have prepared a Jupyter Notebook and it's in Colab, so any of you can have a look in there, but basically it's just step-by-step walkthrough of how would we handle this example with the surveillance application. Here's, for example, how the data frame would look like, the annotated data frame, and here's, for example, the camera blocked image in the synthetic data set. So basically the camera blocked is just a full black image with some random noise added. The camera not blocked is just a white image with some noise added. The door open, here there is a person also, is just a black image, is just a white image. Here the door closed is just basically a brown rectangle. Person present means that there is a head and a body. Person not present means that there is no one in there. The door locked, the lock is basically with a small green rectangle in here. The door unlocked is basically doesn't have the lock, doesn't have the blue rectangle there. Yeah, so if you're interested in exactly how it works, you can open this in Colab and see it step by step with the explanations. Here are all the task flows, so body regression, person regression, full flow, and so on. And this is the important stuff. Once we create the final full flow, which has all the tasks in there, when we say flow.torch, it returns a normal NN module, which decorates all the losses, all the heads, task-specific heads and task-specific neural networks, so that they respect the precondition and the flow is exactly the same as you have described in the task flow. So here, for example, we see sigmoid activation for camera block, door open, and so on. So when we say flow get loss, we get again a loss function which consists of several smaller loss functions. For example, for the binary tasks, it's binary cross entropy with logits, while for the regression tasks, it's a combination of sigmoid and mean squared error. Why sigmoid? Because usually when you're predicting a bounding box, you want to divide the coordinates by the width and the height, and this restricts the coordinates between 0 and 1. So typically sometimes you would want to have a sigmoid activation in the end. So yeah, and this for every different task. For example, for shirt type, which is the type of uniform the person is wearing, there is a cross entropy loss and so on. And then we create a normal module in the usual way we do it. And in this module we say full flow .torch, and then we invoke it in the forward module by including the features that are necessary in this dictionary of features. Then we create our own runner. This creates a special type of runner. It's basically, actually it would be easiest if I just show it. This creates a DNN cool supervised runner, which basically extends this normal supervised runner which comes from Catalyst. And there are several differences. A lot of the arguments are the same, but some of the differences are, for example, by default it's included the interpretation callback is included, which shows you per task the best and the worst examples in the TensorBoard, and it also serializes their indices here, so anytime you can have a look at which are the best, which are the worst, and so on, per task. So yeah, this is the type of runner that is returned here by DNNCool. DNNCool is the thing that sits on top of Catalyst. That basically it's a collection of the utilities that I'm showing today, and I'm just calling it DNNCool. And yeah, basically then we train as usual the runner, and here we're not going to wait for it. I have run it beforehand, and here we can see in the TensorBoard different metrics are logged for different tasks. For example, the loss function is naturally very nicely declining since the dataset is synthetic and it's a relatively easy task. So you can see, different metrics, basically the metrics per task that are defined, and you can see how they move with time, and you can identify potential issues. So, for example, if for example some task is much easier and it gets learned quicker than the other tasks, then here you can identify this, and yeah, that's quite nice. And another thing is the images tab. So here this also works for text, so you can also register converters for text, but here we have for every task the best and the worst 10 examples. It's configurable, you can make this 30 or 50 or whatever. So here you have, for example, the 10 images which were the best for the task camera blocked, which is a binary classification task. And here on the leftmost you see on the training dataset, in the middle you see in the test dataset, and in the validation, and on the last you see on the validation dataset. So here you can, for example, identify some sort of patterns of when the model is doing best and when it's doing worse. So here, for example, maybe let's see the worst camera blocked images. So yeah, it's interesting. So it looks like the worst images for camera blocked are always when you have the door unlocked, and it kind of makes sense because a camera blocked is basically just a full black image, while the door unlocked image, as it is here, is basically a huge brown rectangle that is kind of similar. So I find it very interesting that those are the most those are the worst examples for camera blocked. So it's almost always the full brown image, and it makes sense. Why would it make such a mistake? And yeah, here you can basically see which are the best and the worst examples. For example, for identifying the y coordinate of the face, you can see here that the images are relatively clean. Well, if we have a look at the worst for the same task, you can see, that's really funny. You can see that the worst are actually usually when there is a lot of intersection between the face and the body, and especially if they're of the same color, which makes sense, right? If the head and the body are of the same color, then it's going to be a bit harder to identify exactly where the bounding box for the face is. So yeah, that's I think really interesting and very valuable in a multitask learning project. So yeah, let's go on next. Okay, so now that we've checked out the demo and you've understood how the task flow works, what's the idea of the abstraction, what are some possible applications? For example, if you're monitoring a parking lot, and for example you're trying to identify a particular car or something, first you have to predict if there is a car, then you have to predict the brand of the car, given that there is a car. You have to predict the color of the car, given that there is a car, obviously. You have to predict if the license plate is visible, again given that there is a car. Predict the bounding box of the license plate, given that the license plate is visible, and then do OCR on the section that is identified by the bounding box. So that would be one possible application. Another one would be driver assistance. Here I'm highly recommending the talk of Karpathis at last year's ICML. It was a great talk, and actually it was my inspiration for developing this small library. So example tasks here would be drivable area segmentation, lane detection, road markings detection, environment tags, traffic lights, traffic signs, road signs, static objects, moving objects, children task for everything, like is it for example for every car, is it parked, is the left blinker on, is the right blinker on, is it cutting in. It's lots of different tasks could be needed for driver assistance. Another task would be in NLP. So this is not computer vision specific. In NLP, if you have very different categories, you may want to have different language models for different categories by having the network split based on the category inside the network. So for example, you would have a branch, a binary classification branch, which predicts whether the language is in Russian or in English, for example, and then you have 3 BERT attention layers specific for if it is in Russian, and 3 BERT attention layers specific for if it is in English. And this way we get a multilingual model that still has language-specific subnetworks, but by sharing tokens between languages, it also benefits from both corpora for the embeddings of the input tokens. So here what I mean is, for example, if most of the documents in your corpus are in Russian, and you have maybe occasionally the Java, for example, the token Java, it would have one embedding, but if you include also the English corpus, the Java token would have a really good embedding, because you would have a lot of documents in English for Java, but still you would have Russian specific attention layers in the end. So it would still benefit somewhat knowing the language and even the category. So for example, apart from Russian English, you could easily do this, for example, if you have documents in aviation industry or in IT industry and so on. You can also have a classifier that also does this classification in the network and then splits the network in itself. And another example would be robotics perception. So obviously, if you have a robotic arm that is going to pick up objects, you could have a lot of tasks. So for example, check if the item is of some predefined type, if it is, classify its orientation, color, in general visual characteristics. For example, try to predict suction point for every item given the environment embedding. So the environment embedding would hold information, for example, for obstacles and different stuff like that. And if you're interested in this project, I'm actually writing my thesis on this subject, so you can follow me on LinkedIn. I want to also tell you about the object detection. Basically, anchor-based object detection could be seen as predict if there is an object in this anchor, predict the coordinates of the object given that there is an object in this anchor, predict the bounding box coordinates given that there is an object in this anchor, and then predict the class of the object in this anchor given that there is an object in this anchor. It sounds relatively complicated, but with Catalyst and the utilities that we saw in this presentation, we can get this pipeline and not just do object detection, but we can also customize it very easily. So for example, we can add a binary classification branch if the bounding box is that of a person, and then a binary classifier if he is wearing a mask, and so on. And this is as easy as just adding a call in the task flow. And then we would have all the different interpretations, tree-based explainer, and so on. Yep. And finally, some link. You can find the utilities on GitHub on this link. The first one and the second one is the Colab notebook that I showed you the demo of earlier. And some links which inspired this talk. So yeah, the blog post by Sebastian Ruder from DeepMind, it's a really great blog post. The talk of Andrei Karpati at ICML, and the multitask learning lecture by Andrew Eng. And yeah, this is it. So now let's discuss maybe in the chat what questions do you have, and in general anything that you're interested in. Thank you.